All right. So question 2-3, number 39. I really don't want to do anything with this, to tell you honestly, because it's exactly like the example we did in class last time. What's the key to real? What can I use, first off, to prove this? Squeeze. Exactly. Right? And what's the key function in here that will help me figure out the boundaries for the squeeze theorem?
Cosine.
Yeah, cosine. Because cosine, of course, has its own boundaries. It can only go up to 1 and down to -1, right? So I have naturally defined f of x and h of x, right? My g of x will be this whole thing. It's always in between the minimum of this times this and the maximum of this times this. And what does x to the 4th do as x goes to 0?
Yeah.
So, did the problem for you. You just got to write it down now, all nice and pretty. All right? I love your faces. I would never play poker with any of you.
So we're doing that right now?
No, I'm not. I told you how to do it. And we did an example just like it in class. Right? The squeeze theorem stuff you're going to see can't get that complicated. They can get complicated in real life. Just like the epsilon delta stuff we did. As if that wasn't complicated. That wasn't complicated. It can get complicated. What we did was not. Right? Believe it or not. Because the only functions we really look at are ones that either start off linear or reduce to linear. The linear functions are nice. Doing what we did there in section 2.4 with a nonlinear function can get really freaky. So just try to realize that. Yeah.
Can you also do 46?
Oh, okay. This one's, I like, when you have absolute values inside of a limit question, let me ask you this real quick, a little side note. This is about number, what was it again? 46, section 2.3, right? That's the one about the 1 over x and 1 over absolute value. All right, little side note. What is this if x is less than 5? Can anybody tell me? What's the absolute value due to something that's positive, for example? Doesn't do anything, right? Absolute value forceful. What's the absolute value due to something that's negative? Makes it the opposite of it, right? So really, if I have this, what's the absolute value due to it? Makes it the opposite of what it was. If x is less than 5, and I know the guy that asked the question is like, what the hell has this got to do with anything? Hold on. If x is less than 5, what kind of number is this? Negative. So what's the absolute value going to do to it? The opposite of what it was. So then you get 5 minus x.
That's it.
And try it. What do you get when you plug a 3 in? That's less than 5, right? 3 minus 5 is negative 2. Absolute value of negative 2 is 2. This just says, what's 5 minus 3 is 2. That. Have you guys ever seen that kind of thing before? I mean, that's... Some of you guys are like, yes. So a lot of you guys, no. And that's the kind of problem that seems to be going away. People don't look at that kind of problem. But that's so freaking important. And here's a good example. If you don't understand that, you can't do this problem. So that's my side note. Here's the problem. It says, what's the limit as x goes to 0 from above? There you go. And number 45, notice, is the one with the minus. So we'll look at that next, just as yet another side note. But as x goes to 0 from above, what kind of numbers am I putting in here? Positive. So what's another way to write that then? 1 over x. Because the absolute value won't do a damn thing to you if you're positive. And what's 1 over x minus 1 over x? Yeah, so that limit is 0. For every x above 0, these will always be the same. So they will always cancel each other out. Yeah.
Couldn't you just tell that that was the limit was going to 0 from the denominator?
Well, hell no. I mean, when you first look at this, I'm hoping most of you guys might incorrectly think it's going to infinity, right? 1 over 0 goes towards infinity.
My pre-calc teacher, the way he taught us is, if the numerator is bigger than has a bigger x value, like x cubed over x squared, then it's going to infinity.
I love it.
If the denominator has a bigger x value than the numerator, like x squared over x cubed, then it's going to 0.
Now, the thing you're missing, and I said I love it, but you're missing something. That was discussing horizontal asymptotes, and horizontal asymptotes are all about x getting really, really big. So that would be the limit as x goes to infinity.
Oh, yeah.
Okay, good. That's really key. So you want to be careful. In pre-calc, you very often learn shortcuts for things, and shortcuts are nice, but then sometimes you go to the shortcut without really thinking about what's really going on. So when I plug a number that's really, really tiny, this whole thing should get big. But what's interesting is these are lockstep with each other. When I go towards 0 from above, these are the same. So this gets really, really big, but then this is minus. I'm just as big as you are, so screw you. I cancel you out, right?
So that's why it's 0.
That's why it's 0. Now look at 45. Is everybody cool with that? The key thing there was realizing that you can rewrite that as this because of this. If you don't understand that, you're not going to have a clue how to do that problem. So 45, the only difference in 45 is they say x goes to 0 from below. And in that case, how can you rewrite this?
Is that negative?
Yeah, 1 over x minus 1 over negative x. Of course, what do you get there?
2x.
Yeah, 1 over x plus 1 over x is 2 over x. And as x goes to 0 there, what happens? And it's to 0 from below, sorry. So which infinity are we talking about? Negative infinity. Cool. You guys semi with me?
Yes.
Yeah.
If x is negative, then this is negative, plus this is negative. So it's getting really, really big negative. So that's why it goes to negative infinity. It definitely goes to some kind of infinity, right? There's no question about that.
Yeah, I got you.
It's just that all the values I'm plugging in are negative, so it goes to negative infinity.
So it's going to kind of go like this.
Well, the 2 over x.
Yeah,
2 over x does this, dude. And I'm approaching 0 from below, so what are my outputs doing? Going to negative infinity. Yeah. But again, the key thing is to get here. And you can't get there unless you know how to rewrite that depending on what situation you're in. Which really sucks because they stopped doing it. Stopped teaching that somewhere. Damn it. Sorry. Irks me because then once you get little holes like this in your knowledge, then you get a problem like that. I don't even know you have that hole in your knowledge until somebody says something about it. Okay. All right. Yeah, sorry.
Last one, 61.
Still in 2-3? Oh, yeah. This is kind of funny. So we got what they want here?
Yep.
What's that? So 61 says, show that the limit as x goes to a of f of x times g of x may exist even though the limit as x goes to a of f of x, neither one of these exists. So neither one of these exists on its own, but somehow the limit of the product exists. It doesn't go to infinity, it agrees, everything's nice. So what would have to be true for this to not exist? I mean,
There's a gap.
Oh, there's got to be a...
either it's got to be going to infinity, it's got to be an open circle, something. So, I mean, the kind of functions, I'm not going to... There's a lot of different answers you can give me, but I at least want to get you all in the even. Is that important? Even playing field. One way, if I'm like going to, let's say go to 2. Let's say A is 2. And I've got 1 over x minus 2. Does that exist? No. Right? Or I can have limit as x goes to 3, what do you got? X minus 3, x squared minus 9. Well, does that exist? Yes, right? That exists. So you can't have a situation where it's just an open circle like that. You have to have something where it either doesn't match up, that's harder to do, or you have to have a situation where it's going to infinity or negative infinity. That might be what I try to stick with. So somehow you got to come up with something where they separately don't exist, but somehow together, like they take care of each other's problems somehow. All right, hopefully, you guys kind of see how to think about that. So I want to make sure everybody knows how to think about this problem before you try this problem. This is number 61, 2.3. Yeah.
Is this going to become like a piecewise function or not?
I mean, trust me, there are piecewise answers to this if you want to go that route.
Like, remember when you did on the board like a 1 plus sign and it connected to the cosine of x and how it kind of...
Yeah, but you gotta be careful. This is gonna be the product somehow takes care of it, not another piece of the piecewise takes care of it. So it's, yeah. All right. Something for you to look forward to. But again, this is one of those that's towards the end of the section. If that's the only one you're having trouble with, that's awesome. That means you're doing great. All right? This is not something that just comes to you. But I at least want you to think, what kind of functions would have problems, and which ones of those would multiplying them actually possibly take care of that problem? Like, would I be able to cancel something? That kind of thing. All right. I think I've given you enough to at least think about it. That's 2-3, number 61. I don't want to just give you some answers. I want you to think of something. Yeah. If you can't think of anything, all right. Anything else from... All right, let's do this. I want to do an example of a problem in 2.4 on the calculator. And then I'll see if there's anything else I've got to do from 2.4. Oh, and I also want to show you 2 things. I posted something new on the website, and there's a mention about the Khan Academy, so I want to show you an example video from Khan Academy. Khan. So if you go to my website, this is what I posted, trig identities right here. And if you had me for pre-calc, this should look very familiar. And I actually went ahead and took the tangent stuff down, if you guys remember. So everything above this black line, I expect you to know. I will not give it to you. I will not let you write it down anywhere. On your arm, on your inside of your Coke bottle label. Everything below that black line, I don't require you to know. So if you somehow need it, I'll put it on the test. That kind of thing. Or if you think you need it, you can come up and ask me what it is. Whatever. You with me? So if you don't currently have some of this memorized, get it memorized. So you go to the website, print this out. Hopefully this stuff looks familiar. Right? Hopefully your pre-calc teachers at least made you memorize some of this, if not most of this, if not all of this. Okay.
Kind of.
Kind of? And for example, these things here, if you know these, you can pretty much get these. If you know this one, you can get these two. Right? I mean, there's a point where you don't want to just memorize every damn thing. You want to figure out what's the basic underlying thing that I can build off of to get other things. I don't like to memorize a lot of stuff, and that's not what math is. It's not what it should be. Okay. The other thing is the Khan Academy. I don't have a link here just because I was lazy, forgot. But there's a link here to algebra stuff in my Math 88. So all you do is you go to Khan Academy from there. You scroll down past this, start learning now. All right, look at little Mona Lisa looking at you. And then you go to calculus. If you need to review trig or any pre-calculus stuff, you can go there. Just to show you an example, you go to calculus, limits. If you scroll down a little bit, you see epsilon delta definition of limits. Let's see if I have any sound in here.
In the last video, we tried to come up with a somewhat rigorous definition of what a limit is, where we say, when you say that the limit of f of x as x approaches c is equal to L.
All right, someday I'll actually teach like that. All right, kids, just watch this video. You have any questions? I look forward to that day. Anyway, so there's a stupid amount. I mean, look at all this stuff. And some of you guys, I'm sure, I saw some of you guys are looking forward to doing some science career, so maybe you want to do biology, chemistry, physics. I mean, what's that?
There's LeBron asks. To the right.
LeBron asks.
Is that LeBron James?
Yeah, it is LeBron James. He finds a way to get involved in anything.
That's crazy.
LeBron! Sorry. Alright, so you guys can play around with that. You can look ahead to differential equations. Alright, so that's what I want to show you there.
LeBron asks questions.
Jeff asks, why should I give LeBron?
What is the four people there?
Alright, so what did I want to show you? Most of the homework involves concrete ideas. I only gave like maybe 2 real proof problems in section 2.4. Most of them are like, let's see, what did I actually assign here? 2, 6, 11, 18, 27, yeah. Yeah, so right at the very end I have some, it's a little more than I remember, but I have several that you have to prove. But there are problems like number 6, for example. So we'll do problem number 5. That's like number 6. So number 5 says, use a graph to find delta so that if x minus 5 or 4 is less than delta, then tangent x minus 1 is less than 0.2. So somebody help me out real quick. The general proof is, the general setup of the proof is if x minus a is less than delta, then f of x minus L is less than epsilon. What does that L stand for? The supposed limit, right? The one I'm trying to prove is the limit. That's whatever function I'm talking about. That's the point that's supposed to go towards that limit, right? So the limit is x goes to a of f of x should be L. That's what I'm trying to prove here.
Are you writing those lowercase because they have to be, or like can they be uppercase with the delta and epsilon?
They're accepted to be lowercase.
Okay, so if I were to uppercase, would it be wrong or would it be?
Yes.
Definitely frowned upon.
Yeah. It's sternly frowned upon. But again, it could have been anything. So one part of my brain is like, who cares what I use there? It's just some dummy variable.
Okay.
But the other thing is, epsilon delta proof is huge throughout a lot of mathematics. So if somebody sees something other than that, it's not a good thing.
Okay.
They might do more than frown. I don't know what that means. A math person threatening you is not very threatening. So how the hell do I translate this? This is saying use a graph of this. It's not saying prove anything, because they're giving me a specific number here, so it's a very concrete problem, but it just doesn't have a feel of a concrete problem. So what function am I actually using? What is f of x? Careful.
Tangent x.
Tangent x is my f of x, right? Tangent x. This is just the inputs, right? So I know at pi over 4, tangent is 1. So that's what I'm trying to prove here. I'm trying to prove that the limit as x goes to pi over 4 of tangent x is 1, right? And if you go, I think a few of you guys said you're math majors, when you go into proof classes, you'll be proving things like, and I'm not lying, you'll be proving that 2 plus 2 is 4, for example, using the very, very building blocks of our mathematical number system. So on one level, we already know that tangent of pi over 4 is 1, right? Hopefully. So, but the reason we do this is because we have something we already know. We already know it. It makes sense. And we're just trying to build off of something we already know, and we try to build this weird stuff on top of that. I don't want to have something I don't really know, plus here's some new shit for us to worry about. This double layer of stuff to worry about. Okay, maybe. So the function I'm using.
Okay, so when you move from x to x minus pi over 4 and then went to tan to x minus 1, where was the transition?
So again, the whole idea behind this is, here's pi over 4. Oh, sprinklers. That was such a weird...
Rattlesnakes.
Snakes. No. So, negative pi over 2 to pi over 2. So we got our tangent function. So, of course, pi over 4 goes to 1. So here's the point we're talking about. So I want to know the neighborhood around pi over 4 that will guarantee me to be within so much of 1. Let me just do this. Actually, it would be, sure. So this would be epsilon here. So my scale sucks here, but the neighborhood around pi over 4, that's delta, right? That's how much off of from pi over 4 I am. So how close do I have to be to pi over 4 to be guaranteed to be within, in this case, 0.2 of the actual limit, which is 1, right? That's the whole idea behind this. So this is a very concrete problem, believe it or not. I know everything involved here. I want to make it look like the graph on number 3 or number 4. Right? I'm hoping number 3 and 4 are relatively easy. In case you're one of the booklets, let me put it up here. Which one was that camera? I think it's this one. No input. I think it's computer intuitive. Again, that no input for our. Oh, yeah. Turn on. Yay. So here's number 3 and 4. This kind of problem here. So how would I work back to these here? Right? This is the kind of problem I want to make this look like, and I can use the graphing calculator now. For this one, I want to use the graphing calculator to help me solve this. So I can actually set this up in the calculator and work back to see what these points must be. So if here it's x squared, what input gives me an output of 0.5? Whatever the square root of 0.5 is, just work it backwards. And then what input gives me an output of 1.5? Square root of 1.5, right? So I can figure out what these x values are. So the idea, so in this case, I want to be within 0.5 of the actual limit. So how close do I have to be to the input that gives me that limit? I can work it backwards. I can figure out, well, what's this, and then I take whichever one is smaller, closer to 1, right? Just to be more conservative. You with me? Yeah.
So that's all that question's asking.
That's it.
For those 2 question marks.
What are you talking about? Where's 2 question marks? Yeah. You've got to find these 2 to be able to tell which one's closer. So once you know which one's closer, that's your answer. It says, find a number delta. Once you find a number delta, you're done. That's all that question wants. That's all that question wants.
And there could be 2, and then you can take the smaller one because that guarantees.
Yeah, and I guarantee you there will be 2 because it's a curve. Remember, so if it's a curve, more than likely one side's going to be further than the other. Okay, cool. All right, maybe. So going back to the graph, if I graph Oops, I gotta go all the way back. Graph tangent. I don't need that anymore. So the graph tangent. No, Jeff, go in the graph. Now here's the cool thing about this. Let me just take a step back. Do you see how I want to be within 0.2 of the limit, right? So I want to be within 0.2, so how far up am I actually going to go? Yeah, 1.2? 0.8, right? And then I can actually have the graphing calculator graph these lines for me if I plug them in. So what I want to do actually is I want to do this. I want to say, okay, I'm going to let y1 be 0.8.
Oh, yeah.
Y2 is tangent x. What just happened? Freak yourself. Tangent x. Let me just stick to this. It doesn't like my keyboard. And then y3 is the other side, 1.2. Because that'll graph those lines. So look what it's going to look like. So if I graph right now, it's probably not going to look all that great. Alright, so see my window's all freaky, right? So I can control my window. I don't want to go that far up. Maybe from -1, it's all around 1, right? So from -1 to, let's say 4. And the y from -1 to, because the x I want is pi over 4, so you just go up to 1.5. This pi over 4 is like 0.7 or something. So here's my top. Here's my graph of the tangent.
I'm liking it.
And then here's the, well, I just put them in the other way. So that's the bottom graph and the top. So that looks a lot like that problem did in the book. I can actually see it. And can you see in between these bars is the idea of the epsilon, right? Epsilon is always away from the limit. So I want to work backwards and say, okay, where are my x's? And you can see. Did you have a laser? No. Too bad for me. All right, no laser. You can see right here. Here, if I drop this down, this intersection, that would be that side's x. You with me? That x would get me into this region. That's what I want to do. I want to say, how far do I go away from pi over 4 to get in? So this is one side, and then this will be the other side here. Plop. So if I can just figure out what x's these are, that'll be my range, my interval on the x-axis. So how in the world do I find what x's those are? It's almost too easy now. How do I find that x, that lower x? This right there. How do I find that? Intersection. Right? I've plotted the constant function. I just find the intersection with the tangent. So if I go to, I'll put a little dude. If I go to second calc intersect, go over. Alright, so get right on top of there. So enter. And then now here you got to be a little careful because there's 3 functions in there. So whenever you do intersect, you hit enter, and it automatically bounces to the next one in line. And I want that to be the tangent, so that's why I put it in that order. So it'll start at the top, and then it goes to the next one in line, which is the tangent function. Enter, and then it says, what's your guess? Okay, well I already put it on my guess. Enter. So I get, I can make a better graph here. Which way are you facing? Okay, you're fine. Blah, blah, blah. So right here, I get this is 0.6747, blah, blah, blah. So now I want to figure out what that one is there. How are you guys doing so far?
Good. Isn't, let's just say, theoretically speaking, can't you find that using the slope or the y2 minus 12? No.
No. This is you've got to use the functions you have here. The slope's not going to help you out here.
Okay.
Yeah. And then you find the other side the same way. second count, intersect. Oops. So get on your tangent function. There I am, I'm on the tangent now. Get up here to the intersection, enter, enter, enter. So 0.8761 about. Let me just stop right there for a second. You guys kind of with me? So in this problem, they set up for me what epsilon was. They said epsilon was 0.2 away from 1. So that's why I went to 1.2 and 0.8. So they set that up. I got to work backwards to see what delta might be. But I got two candidates. Pi over 4. Which one of these is closer to pi over 4? I don't know yet. Pi divided by 4 is that. So if I do that, minus 0.6747. This candidate for delta, this side here, would be 0.1107. Now what about this other side? What's the other candidate for delta? So now you just do 0.8761 minus pi over 4. 0.0907. So which one are we going to pick? Yeah, this dude. So that's going to be our delta. That's it. That's the end of that question. Right? They said find a delta so that when you're that close to it on the x-axis, you must be within this on the y-axis. So if I pick the smaller one, I'm definitely going to be within it. Because this guy says I can go all the way down to here. So he can definitely handle just going that far down. He's definitely going to still be in there if you just go that far down. Yeah.
Will they do the opposite and give you the deltas and you go?
Yeah, and in fact, I think we did a problem like that. Very first thing, we did one that way. Yeah, I think so, if I remember.
Will they give you one delta and one other thing?
No. Yeah,
Do you have to add the delta to your original x value, or are you done at this point?
done. You found the delta that makes this true. That's what you would fill in here to make this a true statement. If this is less than 0.0907, you're guaranteed that the distance between your output and 1 will be less than 0.2. You'll be in that area there that those two lines define. Okay. And this is obviously one of the hardest things to get down in the early going of calculus, is this epsilon delta. In fact, it's so hard, and you're thinking to yourself when I say this, damn it, why didn't I find out who this was? But there are teachers that don't teach it at all, and they suck. Unequivocally, they suck. Because then they set you up for failure if you're going to go further, and then all of a sudden they're talking about epsilon delta. You don't even know what the hell it is. You've never seen it before. I'd rather have seen this and go, I'm not sure what the hell it is, and later I'm like, well, at least I've seen it. You know, instead of like, what the hell is that? All right. Any specific questions from that section 2.4 before we keep going? I mean, you just got to get in there and try it. Yeah.
So how would you, it's not a specific question, but how would you work the problem? Would you work the problem the same way if they gave you the deltas?
If they give you the delta, you just you figure out what those x's are, plug them in, and then you see what the outputs are. So it's just really in reverse. It's actually easier.
Yeah.
You know? Yeah.
So after you find the 6.67 and the 0.87 stuff or whatever, what is the next step again?
Well, where'd these come from?
Yes. Yeah. After.
Where'd these come from? What are those? The difference between pi over 4
And then number.
and the number we got there. Yeah?
So you take the number and then you put it into that.
So pi over 4 minus this
Okay.
is there, and then this minus pi over 4 is there. And it's curved, so I know it's going to be skewed. The interval's not going to be symmetric. So that's why I take the smaller one. Okay.
So for the first one you do pi over 4 minus, the second one you do that one minus pi over
Yeah,
4.
you just take the endpoints minus whatever, the actual value is that you're curious about. Yeah. Okay, maybe.
I bore you with asking you to go through, I understand how to get it all, but how to read what's in the purple up there. so I understand what's going on.
Oh, okay. Find delta so that if the distance between an input and pi over 4 is less than delta. So I can read it directly, and then I can read it in terms of what it really means.
That's what I mean,
Right?
yeah.
Okay. So, and again, this is the whole idea behind epsilon delta, the whole idea behind limits, is I should be able to, given some value here, this is kind of like what this skips, because it's not really a proof. They don't start off at the right place. Given some values, if somebody came along and said 0.2, I want you to be within 0.2 of 1. Can you do it? And we're like, yeah, we can. Look, we did it. So as long as all my inputs I use are only this far off from pi over 4, all my outputs will be at most 0.2 away from 1. That's what that means. And that really captures what this is saying. I don't know if it was too fast, but...
No, just go through it. I understand what you're saying.
Well, that's it.
there.
I mean, that's it. In order to make this difference less than 0.2, meaning in order to make my function outputs...
That's your function, Tanner.
Yep, tangent x what is the function I'm using.
-1.
The 1 is the limit, right? So this is
yeah.
this guy here is this guy here, right?
Where does the pi over 4 get incorporated into it?
So again, the thing behind this is this,
Oh, got it.
right? As x goes to pi over 4, the tangent x should go to 1. What does that really mean? That means if I get really close to pi over 4, then I should be getting really close to 1 on the output side. That is the ultimate shortcut way to say that. And that, of course, is just what a limit should freaking mean. So if I pick the wrong number here, and I get somewhere close, it's going to not work. It's going to be going around what the real limit's supposed to be. So if I thought the limit here was 1.1, I'm going to make this get so small, and then 1.1 is going to be left out. It's going to be, already 1.3 won't work, right? So if I thought the limit was 1.3, right here, that shows me, no it ain't.
Are they always going to give us those two, the pi over 4 and the limit, or are we later on going to have to be...
They're going to give it to you. Yep. Don't worry. And again, this is an example of something that we use to prove limits. When we really want to dig down and make sure that what we're doing has a good foundation, we use it to prove limits. We're not going to expand on this really that much in this class.
So technically, you would have to go through your plug and chug chart thing, get that number, and then to go back and use that to prove that your plug and chug is correct. Is that kind
Yes,
of a
good.
roundabout way of saying
I like it. So if you had some funky ass function here, you're not even sure how to, you don't even want to start to graph it. You get some kind of idea what this might be. And then you actually go through the proof. This isn't even the proof. This is just a concrete example of what these numbers mean, right? How they interact. You go through the proof to really prove it then. But you could do that way, yeah. Good. Yeah.
And they'll always give us the 0.2, right? Like the delta or whatever it is, 0.2.
And let's do one example of a real proof where they don't give that to us. Right? This is concrete. Here's a proof.
delta's the top and the O 2.
Okay. So like number, let's see, number 20. Looks disgusting. Let's see. There's no way to say what I'm about to say correctly. So I'm just going to say, if you have a lot of trouble with this, do not tear your hair out over this. This is important. It's used to prove limit laws more than it's used to prove specific limits, to be honest. Right? Very often we use these theorems and these ideas to prove other theorems and ideas, so then we can use those other things. So the limit laws, this limit law here, remember this thing? Where you can basically just take the limit of each piece? And it was kind of like, it felt like, well, duh, you should be able to do that. You can use the proof that we're about to do to prove this is true. And they actually have it spelled out in that next section. They have it spelled out. But let's try this in proof form. So somebody help me out here. What's Let's identify all our players. What's f of x? And what's L?
F of x is 3 minus 4/5 over x.
I like it. What's L? Negative 5.
Oh.
Right? So we're saying that the limit of this function is that. That's the L. That's the limit. That's the function we're dealing with. What's going to eventually go into here?
That means 10.
10. Good, because x is going towards 10. Right? So it's kind of good to identify those parts before you really jump into this. Then we have side work. I'm going to use this for the proof. So here's the side work. All right. So the and I don't know how you're going to do this in your notes, but it will. The proof would involve given epsilon greater than 0. Let delta equals something so that when x minus 10 is less than delta, 3 minus 4/5 x minus negative 5, right, minus L is less than epsilon. Right, so that's what we have to use. We have to come up with what delta has to be in order to make that work. And delta almost always is based on epsilon.
Is that, isn't it 5?
Negative 5, yeah.
On your x minus 10 is greater than
Oh, that's delta,
Delta
yeah.
or 5?
I know. Is that any better?
Yeah.
Okay.
Damn it.
All right, so the side work. Now, and again, this feels like cheating in a way. But we start with where we want to end up. And we work backwards to construct the delta that will work. And this is called, incredibly enough, a construction proof. We construct the thing that will do what we want it to do. So we're not doing anything illegal at all. It's nothing. I can start here if I want to, just play with it. And if I happen to stumble upon this, great. Then I know what delta is going to be. And for lines, that will always work. That's what I was meaning. If I use linear functions, this is easy. I can always recover this. If this function is not linear, I maybe have to do some magic to make this pop out. Or a lot of assuming to make this pop out. So here, if I start with where I want to end up, that's a plus 5. So what's the next thing I can do in there?
3 plus 5.
I love it. So I got 8 minus 4/5 x less than epsilon. Does this have any fractions in it? So how do I get rid of that fraction? Multiply by 5. And I can multiply by 5 because it's positive, right? So the absolute value is cool with it coming inside and outside. So if I multiply by 5, I get 40 minus 4x less than 5 epsilon. And what's really cool about 40 minus 4x? It's almost this in a way, but I like this problem because it's a little bit backwards. It's cool. I love it. So if you divide by 4, you get this. Now what's not quite right about that, but hopefully some of you guys are not bothered by that. Is that the same thing I've got here? It's backwards, but the absolute value doesn't care, does it? What's the absolute value of 2 minus 5? 3. What's the absolute value of 5 minus 2? So these absolute values don't care. So then x minus 10. That's one example of a very simple magic trick, right? And what I mean by magic is just adjusting what's in there using legal math manipulation rules, right? Absolute value maintains a positive, so it doesn't matter which one comes first for absolute values. So what am I going to let delta equal then?
5 over 4. 5 epsilon.
5 epsilon over 4. Which kind of makes sense. Think about it. If this guy comes in with an even smaller and smaller epsilon, I am going to want to make my delta smaller and smaller, so I still end up in that little area he's given me to work with. Does that make sense? That's why delta is almost always dependent on epsilon. So now to do this, now here's the awesome part. Here's the side work, which actually, if some of you guys would do that and not even show it to me, that would kick ass. Don't even put it on your paper. Then you come over here, you say, let delta equal this, so that when this is true, so I start here, and now I go forward. When this, so I got to start here. Start here. And delta, of course, we're letting equal 5 epsilon over 4. And then we just basically do everything we did there backwards. But that's the requirement for the proof. To prove this, I say, when this is true, start here, show that this is true. And of course it's going to work. We just guaranteed it's going to work. So if this was the wrong guess, this side work would never work. It would kind of crap out somewhere. That would be telling me, oh shit, that's the wrong guess. That's not the right thing to use. Does that make sense?
Yeah.
Linear functions are too easy. That number is the truth. So the fact that I put -5 in there, minus -5, is what makes this pop out so easy, right? It's always going to work for straight lines, as long as that number is the right number. If I put -6 in there, I ain't never going to get to 10 minus x. It's just not going to work out. You guys semi?
So where do you go from there?
All right, so now we keep going. Multiply by 4. Divide by 5. Is that cool? Multiply by 4, divide by 5.
Is that what I just did?
In reverse. This is with the part that feels like cheating.
Oh, yeah.
We did that in reverse just to get an idea of what delta should be. But the proof says, when this, then this. So the real proof has to be start here and go. But how do I get that? Go backwards. Side work. That's not part of the proof. That's just us constructing what's going to work. And then we show it works. Now here, of course, we got the problem with these are backwards, right, from what it's supposed to be. And also I want to recover the -5 piece. I want to just make it look like this. I've got to recover my function. So first I turn this back around again. And then I'm there, right? So, and again, this feels like cheating because we're like, we did the work. Well, that's cool. That work we did. So it should be easy to do this work then. It's based off of that. So then I get my 3 minus 4/5 x minus -5. Check. So when this is true, then this is true. Done. When I am this close to the, when I'm this close to 10 as an input, I am arbitrarily close to that as an output. Yeah.
So pretty much after you finish your side work, you just gotta write it in reverse and then you're done.
You got it. And again, it feels like cheating. And I was trying to explain to somebody who came and saw me earlier, lines are almost too easy of a function. If I try to go one step up in degree and go to parabolas, to quadratic functions, they would be almost too hard of a function to really see what's going on here. You with me? But it is still good to see it. I just don't want to take the time right now to do it. I mean, it's really neat what you have to do. Part of me wants to do it, but we don't have time. Yeah.
What are they expecting you to do to find the delta if you're not supposed to do the side work?
No. You have to. It's just that this is not part of the proof. The proof says, given epsilon, let delta equal something. Okay, I can't even start the proof off until I know what delta is supposed to be. So that side work tells me what delta should be to make this work. So the proof requires me to have this to get the proof going. The side work gets me what that's supposed to be. So I mean, this whole thing together is the proof, but this is the real body of it. This is what's required to prove it. That's just me getting this piece of it.
Okay, so that, I mean, technically that is part of the problem.
Yes, that's part of the problem, not part of the proof. I like it. Yeah.
Like, how do you even make sense of 5 epsilon over 4? Like, what is that?
So if somebody
Is that
came
like a
along,
number
now watch.
figure? Like
Watch.
5?
I'm with you. Huh?
Is that like a number figure? Like is it a number?
If somebody, remember, what's the whole idea here? Somebody comes along and says, I want you to be this close to the limit. They can come up with their own
Yeah,
epsilon.
we always had numbers.
I know. But this is a proof. Anytime you use concrete numbers, it's not a proof. Because what if I made it smaller? What if I made it smaller? Maybe you just got lucky and you got in there, even though that's not the right limit. Maybe you just got lucky to be in there. You kind of with me?
Yeah.
This says any epsilon. Think of the smallest number you can, and then cut it in tenths. And then cut that in tenths, and then cut that in tenths. I mean, that's the smallest possible number.
Oh, so it's kind of finding the formula.
It's proving it using the idea of epsilon without having to plug actual numbers in here. Because you can never, if you think 1 over a billion is small, you're wrong. It's not small. It's huge compared to 1 over a billion to the billionth power, right? So epsilon, and that's huge compared to blah, 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 blah. You can keep going. So epsilon says, let me get as small as possible without you having to actually plug that number in, because I don't know what the hell that number is. That's what this proof really does for me. And real quick, if somebody came along and said, I want epsilon to be 8. That's pretty damn big for epsilon, but what would we make delta equal to then?
8 times 5 divided by 4.
Yeah. 10. Right? So if somebody said, I want epsilon to be, 0.01. Delta would be 5 times 0.01 divided by 4.
Okay.
Whatever the hell that is.
So that means that delta can go 10 left and 10 right?
Yeah, that means to be within 8 of the limit, I can let my inputs be within 10 of, in this case, what was it? 10. Within 10 of 10. So it'd be from 0 to 20. Does that make sense?
Yeah, because the slopes. The slope.
Yeah. So are you guys semi with me right now?
No, yeah.
These are good questions, because for this example, let me see what can I get rid of here. Oh, let me try to work up here. For this example, let me see where am I? Our outputs are around 10. So for epsilon equal to 8, I'm sorry, I think I just said it wrong. It's 18, 2 to 18. Does that make sense? It's within 8 of the output. My input can then be within 10 of, oh, that was cool. That was the other way around. Stop it, Jeff. The output's supposed to be negative 5. So I can be within 8 of that supposed output. So I can be up to 3 and down to negative 13. So that's my epsilon right there. Cool? For the 10, for the inputs, I found out that I have to be within 10. So from 0 to 20. So when I plug a 0 into that, what do I get? When I plug a 0 into the function,
3.
I get 3. Hey, that's the max I said it could be, right? When I plug a 20 into the function, what do I get?
Negative 13.
Negative 13. And it's because it's a straight line that it's going to match up. And, if I have some kind of a curve, it's going to be in here. It's not going to be the exact endpoints, but it's going to be inside of those. It's going to be in here. For a straight line, you're always going to get the exact endpoints.
Like what do you mean, not the exact endpoint?
If it was a curve, then when I plug in those, it'll come out to be 1.7 and negative 8, it has to be inside there at most equal to the endpoints here.
Gotcha.
Okay. All right, that's plenty. That's enough. All right. Let's see. So I definitely try to get through 2.5. And the nice thing about 2.5 is we've basically been talking about it this whole time. I keep saying the word continuity before we even got to the continuity section. Who remembers the condition that you need met to be continuous at a point? I've said this a couple times. If the limit exists somewhere, what could happen at that point? Let me put an example up here. For the limit to exist,
There could be a hole.
there could be a hole. I love it. So for the limit to exist at a point, there could be a hole here. So the limit exists because the bottom matches up with from the top, right? From below matches up with from above.
Did you say, like, you draw, keep your hand, keep your...
That's for continuity. So for a limit to exist, all you need is the limit from below. Do it, Jeff. There you go. To equal the limit from above. That's all you need. For it to be continuous, now let me go over this idea. What could f of a be? It could be not existing, or it could be here and there and there. That's not going to screw with this thing, right? The limit doesn't care where that is. The limit just says it looks like it's going to whatever that is, right? That. Let's just say it's L. So let me just stop right there. You guys with me? That's the whole idea of limit. For it to exist at a point, from above and from below have to agree.
Now, is this continuous?
Not yet. Not yet. For it to be continuous at a point, what's the extra condition that I have to have happen?
Should equal L.
Can't pick up your pencil.
I like that. Can't pick up your pencil, but talk more in terms of what I have up there. I think I just heard somebody say it.
There can't be any holes or any jumps.
So in order for there to not be a hole,
A needs to equal F of A needs to equal L.
I love it. There it is. Right? The function has to be defined there, and it must equal the limit. Fill in the pothole, right?
Yeah.
How do you fill in the pothole? You let f of a equal L.
Or the next one.
All right. Stay alive. You can make it. So for continuity, then, this is the requirement for a limit to exist. For a limit to exist at A, that's all you need. You need that to equal some L, to exist, equal some finite number. For continuity, you have to have the limit as x goes to A of f of x to equal f of A. Let me let you just absorb that for a minute. That one statement says a lot.
So continuity and limit aren't the same.
Continuity uses limits to define, we use limits to define what continuity is. But just because a limit exists somewhere doesn't mean it's continuous there, right? Yeah.
You can have a limit of A negative and A positive. They have two different L's.
But the limit wouldn't exist.
Are you okay? Okay, you're saying that definition you have written on the board only applies to the graph you have written on the board.
No. In order for a limit to exist at A.
I missed the at A part.
Yeah, that's the title, but I should write that down too. You're right. For a limit to exist at A, these two have to exist and they have to equal the same. They have to equal the same thing. Continuity just adds one more requirement. It says
No holes.
you got to fill the hole in, right? If there is one, right? The function value can't be wherever it wants to be. It actually has to equal L. So look what this really says. It says the limit exists, which means the limit, it's the same from both sides. It says the function at A exists, and it says that output equals that limit. It says those three things very concisely, right? That kind of thing really gets math people going. Look at all the shit I said really quickly, right? That's basically a lot of math right there. And that's basically you can just say if I can draw it without picking my pencil up, that's the same thing, right? So let's get a little bit deeper into continuous functions then. What's kind of not fair about a function, talking about continuity of a function, if it's only defined up to a point like that, and this side just keeps going? It's continuous everywhere, isn't it? But what about at the end point? Technically, by what we've written so far, can it be continuous at the end point?
Yeah.
Because how can a limit exist there if there's no other side? So thankfully we have the idea of continuity from below or from above, which personally any endpoint, you don't have to include from above in this case, or from below if it was over here. All you need is everything working from that side. So in this case, continuity from below would say, how many dots do you need? The limit as x goes to 5 in this case, right? From below has to equal f of 5. It's not a big leap to take from that, but that's why we have these. If you're looking in the book and you're wondering, why do we have continuity from the left and continuity from the right, or below and above, it's because of that situation. That's the only way to make it fair. It's not this guy's fault that there's nothing existing over here. He should still be continuous in the same. Every point's continuous, except that dude. That doesn't seem fair. All right, so then we just say, okay, he's cool because everything's good up from that side. Is that all right? Okay. And then we have a couple of nifty theorems about.
I got one question for you.
Yeah, sure.
You may be getting into it later, but so what if the line has a dot on both ends?
Then that's fine. Then this would be continuous because it's okay from below. This one, if this was a dot, then it would be continuous because it's okay from above. Same thing. So continuity from below, and I'm implying that there's also, I just don't want to write a line. Continuity from above would work in the same way. Yeah. So if that was there, same thing, just from above. Yeah, I like it. Yeah.
So would you just say that is continuous, or you have to say?
And see, this is the cool thing. This is one area where textbooks and teachers might actually disagree with each other. Me, I'd say it's continuous at that point. It's continuous at every point on its domain. That's what I would say. Some people would argue with that. And I'm like, yeah, whatever you want to do with your day. It really truly doesn't matter. It's not even going to affect anything further along, like some bigger, more involved proof. It's not going to affect anything. It's just some silly thing to get wound up about that really doesn't mean anything.
So if the point at 5, like say f of 5 equaled not that point, then it wouldn't be continuous, but there would.
Yeah, if this was if that was an open circle and then it was like there, then it has the problems we were talking about before. So every problem that the other thing couldn't have, this has to not have those same problems. It just doesn't have to have the thing from the other side because it doesn't. It's not there. So it's not fair. Is it continuous because there's nothing there? So how could it not work? There's nothing there to not work. Does that make sense? Yeah. All right. Here's another kind of function. What situation might this function exist in? Actually, it's more often it would be curvy. What kind of situation might something like that show up in?
Let's say dosage to a medicine.
Yeah, and that thing would sort of be curved, showing that it would be the same idea, just be curved, and then you inject it, so then it jumps up, and then it curves down a little bit.
Oh,
so that would look more like, you're right, that would look more like this, and then you inject, and then you inject.
Could that also be the medicine still in your blood, like about min and max of what could be milligram wise of what could be in
That's the
your
idea.
blood?
So this is over time, the amount of medicine in your blood it's decreasing. And then you get an injection, and then it's decreasing, and then you get an injection, or you take a pill, whatever. Yeah. Okay. And it'd be a little more complicated than that, but that's plenty for that. Where else might this kind of thing show up?
Shipping rates.
Yeah, where something anywhere from 0 to 9 pounds is this much, and the minute you hit 10, suddenly you jump up by a certain amount, right? You guys with me?
Wait, what is it? Cost of shipping.
Yeah, and there's a lot of situations where like if you could just hit 10, you'd be golden, but you didn't. You hit 9, you're like, damn, I can't get to that next level, so it just jumps, right? So we see that kind of thing a lot, like calling somebody on the phone, having somebody come to your house to fix something. Maybe they have a set rate per hour, or any part of an hour there, or child support, right? So this kind of thing shows up. So this is another situation where we talk about continuity from above, continuity from below. So where would this thing be continuous? Obviously anywhere on the line, but which side, like this guy? Where is he continuous in addition to that? Is it continuous there?
No, that's
Because the function is not defined to be the same as the limit would be from below, right? But he's okay there, isn't he?
yeah.
The limit from above is the same as the function value. You guys with me? So it's another place where this idea could be used to make it more fair, right? Yeah.
When I ask this, are we ever gonna have to like define what kind of discontinuity it is? Can we just say it's not continuous?
No, we're getting into the names of
Okay,
it.
so that's considered like jump discontinuity, right?
You gotta love the names. This is one case where the names actually kind of make sense. Even if you forget it, you're like, well, it jumps, and you're good. So this would be specifically called a jump. Yeah, discontinuity. Right, that's your classic discontinuity.
So, because that hole's not filled in there, it's not continuous at 1, but
Yeah, this is not continuous at 1.
like 0.9 is continuous. Like
How many
right.
From below, it's not continuous at 1, but from above, it's continuous at 1. Let's be careful how we say it, yeah. From below, it's not continuous at 1,
Oh,
is
but
it?
above.
Because the limit doesn't match the function value. Function value's up there. So from above, it's okay
Okay, gotcha.
at 1.
But at 0.9, is it continuous from above?
Yeah, anything in the middle here is fine because it's fine. It's in the middle. So there's points on one side of it, points on the other side of it. It's just the end points that would have a problem. So in symbols, the limit as x goes to 0 from above of f of x. What would that be? What is the limit as x goes to 0 from above? 1. And that's the same thing as f of 0, right? Because f of 0 is 1. So therefore, it's continuous from above at 0. What's the limit as x goes to 1 from below?
0.999.
Nah, come on. What's the limit as x goes to 1 from below? 1. It's 1 the whole damn way along, right?
But the continuous is.
Is that equal to f of 1? No, not equal to f of 1, because f of 1 equals 2. So it's not continuous from below at 1. And each time you step up to the next dumbbell here, it works the same way, right? This side is okay from above. This side is not okay from below because it jumps up again. Again, that's getting way too deep into this. Yeah.
So it's like the same idea as the limit from below or above, right?
And it's just adding in the requirement that the limit has to actually equal the function value there. That hole's got to be filled in right there.
That function is not continuous, right? But if you break it down
Yes.
from below...
So you can talk about a function being continuous on certain intervals. So you can either have a function continuous, like sine x is continuous forever, right? Or you can have a function like this that's continuous on intervals, right? So you kind of break it up. It sort of looks like a piecewise function anyway, so it should be, each piece I should be able to talk about its continuity. Cool.
You don't care that at the starting point of, say, the bottom of the dumbbell, you don't care that the starting point, because you're coming downhill, you don't care that the starting point is open, because you're only worried about where it's ending because of what you wrote.
Yeah, all I care about when I'm talking about continuity and limits at a point, I'm just worried about near that point. And when I say near in math, I mean damn close, right? So I don't care what's going over there when I'm talking about there. Is that what you're saying? I don't care that that's open when I'm talking about the continuity
We
here.
care about not near, we care about it's got to be there.
Yeah,
That's the function of.
that's true. Exactly. So I don't care what's going over there when I'm talking about right there, yeah.
If you were going from the negative side, you were going this way on the first one, the continuity would stop at like 0.9999, right? Because it doesn't reach 1 because there's a hole in it.
All right, be careful. Continuity requires that what it looks like it's going towards is actually what it gets to. So on this thing, it looks like it's going to 1. But at 1, what does it actually get to? 2. So there's no 0.99 discussion in this, right? Continuity is built off of limits, and limits don't go to 0.999.
Right.
Yeah. Okay.
What it looks like it's going to.
Yeah.
And then you have to prove that it's going there with the function equals 0.
Okay. Then we have this. Blah, 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 blah. Okay. BLAH. If F and G are given. Okay. So the theorem, the next theorem, real quick. This is theorem 4 on page 121. if f is continuous near a, I want to use the same, or at a, yeah. But really near a. And g is continuous near a, then all these things are true. And I'm not going to write them all, but you can see f plus g is also continuous at a. F divided by g, f times g, f minus, all that stuff, they're all continuous at a. Which kind of makes sense. If one function is okay at a point and the other function is okay at the same point, then the combination of those functions are still good at the same point, right? Obviously, with the division, you can't have the g function be 0 there. That's the one thing this can't happen. So that theorem is nothing major. It's good to know. It's nice to have. So we can, if we know, so sine x, is that continuous?
Yes.
Yes. I'll test you out. Square root of x plus 2, is that continuous? On its domain. Whenever I say something's continuous, I'm talking about on its domain. So what does square root look like? That one specifically is going to be transformed back to. It's going to look like that. Does that have any continuity problems anywhere? Especially considering that we're nice to the endpoints, right? It's continuous, isn't it? So a continuous function plus continuous function, so what about the whole thing? It's also continuous. In this case, at every point on the domain. So what would this be? Continuous where exactly? This guy has some problems, so it would be continuous from -2 to infinity. Right? Because, of course, this way past -2, you can't talk about continuity of this. So when I say a function's continuous, I really am implying on its domain. Okay. So obviously, the nicest functions in existence are continuous everywhere. And those would be polynomials. Yeah?
Is there a time where we talk about it being continuous on the range?
No. You could do that if you're talking about inverse functions, because then your range becomes your domain, but then essentially you're still talking about domains. So notice that very often we're talking about domains when we're talking about characteristics, because that's kind of like where things happen. So when I say where is it continuous, I am automatically talking about its domain. The range doesn't really matter in terms of these things we're talking about. It can do whatever the hell it wants to, right? When you start talking about inverses, then you could possibly talk about that, but why not just invert it and then talk about that inverse's domain then? Instead, so that, yeah, that's the one place it would make sense. So let me just get down to it. Theorem 7 has all this. This is really cool. This is on page 123. It's a listing of all the kinds of functions that are continuous on their domain. So when I say a rational function is continuous, that means on its domain. So any rational function any rational function will be continuous on its domain. So obviously this guy has some problems at a couple spots. Right? Can somebody describe to me what's going on with this thing? It's a bit of a review from pre-calc. Where's it got problems?
X minus 1 is minus 5.
Okay, cool. And of course, the top, you got to be a little careful. I'm a little evil here, but oh well. I can be evil to you guys. So, which one of these is going to be a true vertical asymptote? At 5, it's going to be a vertical asymptote. At 1, it's just going to be a hole. Right? So at 1, it's going to have a hole. And at 5, it's going to have vertical asymptote. Right? You guys semi with me? Is that cool? So at 1, it wants to be, let's see, at 1 it wants to be a 2 over -4, so it wants to be a -1/2 at 1. So at 1 it's going to have a hole right there. and then whatever the hell it's doing, right? But anywhere else besides those points, it's kind of like, if it's not even in the thing's domain, it's not really fair to count that. So it's not in this guy's domain, but on everything else, on all the other points, I'm too tired to even worry about what this thing really looks like. You can still do it, Jeff. At -1, it's got a, so it probably looks something like this here. Sure, well. So everywhere else, it's continuous. Every other point on there, except for that one, and at 5, at 5 it doesn't even matter. It goes to infinity, negative infinity, right? So it doesn't really matter there. So every other point on here, it's continuous. Okay, maybe.
So the domain of that equation was all real numbers except for x equals 1 and x equals 5.
Good. So if I gave you this thing and I said, where is this continuous? You would say everywhere except that 1 and 5. Yep. Because that's not in its domain. It's continuous on its domain. So you just have to exclude whatever's not in its domain. Okay,
Because there's a vertical asymptote.
Yeah, so at 5, it's not continuous. I mean, this is the worst extreme case of non-continuity. This thing goes to infinity, and then somehow you take one little step over, and you're at negative infinity. Do you see what I'm saying? So they so don't agree. There's no damn way in hell it's going to be continuous. There's nowhere even near being limit existing. So at 5, it's out, but everywhere else, if I wanted to, I could keep drawing this thing, right?
Up.
Forever. Just somebody keep putting more and more paper back there. I can keep going for the rest of my life, up past, out of our solar system. So, and I wouldn't have to pick my pencil up, would I? Or my pen in this case.
Maybe you get a new one.
But of course, we do. Yeah, hopefully I have a little supply. I'm not really planning this out, thankfully. You see, I'm going to need a backpack.
Super sick expo. That's
Infinitely a large backpack with an infinite supply. All right, screw it. I really want you to understand, because, I mean, you could argue that I had to pick my pen up to come down here, but I just do that because I really don't feel like going forever up. But that explains why at 5 it's discontinuous, because what I have to do, once I get to infinity, then I come back down here and negative, I got to pick my pen up. It's discontinuous at 5, because I had to pick it up to get to the other side. Okay, that's enough of that. Okay. I love you guys. It's better to overanalyze than under. And we are definitely a group that seems to want to over. That's good.
That's the whole theorem 7?
Theorem 7, and I didn't write it all down, but it just, all those functions it says, polynomials, rational functions, root functions, trig functions, inverse trig functions, exponential functions, and logarithmic functions, they are all continuous on their domain. Every point that you're allowed to plug in, it's continuous at that point. Good to know. Right? Blah, blah, blah. And really, where that comes in handy, we've already used this fact. Remember, what can we do with this? Let me see if I can freak some of you guys out.
So what type of function was that last one that we just did?
Rational. Yeah, because it's a ratio of polynomial functions. Yeah. So it's the second one in, I think, the list, right? Cool. Somebody help me out here. Don't overthink this. What do you know we're allowed to do here?
plug in 4.
So what is it?
-4.
So overthinking. 4 squared? Minus 16? Square root of 0? 0. Now, this is and I really kind of didn't make a big deal of this, but root functions are continuous everywhere on their domain. If it's continuous, that's the one time you're allowed to plug that in. Because what does a continuity mean? How does it relate to limits? If it's continuous at a point, that means the limits are the same as the function value. So if the question is a limit question, and this is a continuous function, plug the damn thing in. It's defined to be the limit. If you plug that in, the function value will be the limit. So that's why that's my answer to the limit question, because the function value is the limit. It's continuous. So we've already been doing this, but now it kind of comes to, oh yeah, now that's why we're allowed to do that. All right? Okay. Maybe. Blah, blah, blah. That's all. Okay. So what is some homework from here going to look like? It sounds kind of wide-ranging. So let's see. What's homework going to look like? Oh, yeah. Here we go. You know to expect questions like, what can you get to? Questions like that. So you kind of focus on the problem points. I mean, wherever there's a line, there's no problem at all. So you kind of immediately focus on things like this. Obviously, at -2, it's discontinuous, right? Because not only does the function value not match the limit, there is no limit to talk about. The limits from both sides don't agree, right? So, good. 4, it's discontinuous because the limit does not exist at 4. Right? You can argue that they agree, but they agree that it doesn't exist. It goes to infinity, right? Cool. And 2, functions defined there. The function equals the limit from above, but the limit doesn't exist. Why? Because this from both sides it doesn't agree, right? Second problem should be pretty quick. You can see where the discontinuities are, and then you can think, okay, can I explain why in the terminology we have here, right? The limits don't agree, the function value is not defined there. I wonder if the other problem has something more interesting. No. Yes. If I could just get there. Screw it. I got there. All right. Bear with me. So, at -4 is a continuous. Exactly why not? Yeah, function value is undefined, so it can't even equal the limit. Then does the limit exist at -4?
Yes.
Yes, why? Because the limits from both sides agree. So the limit existing at a point has no restriction on what actually happens at that point. Because the whole idea of a limit is you never get there. You just see, where does it look like I'm going, right? So the limit doesn't care what's happening in -4. All it cares about is, oh yeah, they agree. So the limit there would be, okay, whatever the hell that is. Great. Blah, 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 blah. Nothing else really interesting there. At 4, that's excessively funky. The function value is there, but of course the limits don't agree. This one doesn't even exist, right? This limit exists. This one doesn't even exist. It has no chance to be continuous there. Okay, cool. So very often it's easy to tell where the discontinuities are, and then you just take a second and figure out how to explain why it's discontinuous. Which part of it does it lose? Do the limits not agree? Do they agree, but the function value is not there? You know, that kind of thing.
For like -2, it's continuous from below, right?
I love it. So if they were asking, let me see, does it say from the graph state the region? Ah, cool. Whether f is continuous from the right or from the left or neither. I love it. Cool.
Okay.
So like you're saying, in -2, does it have a chance to be continuous from either side? It's obviously not from this side. Is it possibly continuous from this side?
No.
Why not?
Because there's gap.
Function's not defined there. So which one actually has a chance to be continuous from one side or the other? This guy. And he's continuous from below. Because his function value actually is the same as what the limit looks to be from that side. You with me?
But doesn't he have a hole right there?
This guy doesn't have a hole.
I'm talking about,
I'm not talking about him right now.
no,
So
to the left.
here,
Yeah.
again, I'm not talking about him at all. I only care about stuff happening right next to this guy. Right? So I'm talking about from below, the limit is this, and the function value is the same thing. Therefore, that's continuous from below. Where else is continuous from one side?
From the above or the positive side of that last one.
4.
All right, so from above for 4, and of course from above for 2. I love it. Cool. Right.
So even if it's a line and it has a hole in it, it still can be continuous?
So this is definitely discontinuous in -4. But the minute you get past that,
Right.
you're fine. And then you're even continuous here as long as you're saying continuous from below. Now, are you continuous at -2, period? Hell no, because both sides don't agree and all that kind of stuff, right?
Yeah.
But if you want to break it down even further, say from below, it's fine. Because what it looks like it's going to is actually where it gets.
From above, it's not fine. Right?
From above it, it's bad. Because it looks like it's going somewhere and it doesn't get there from above. So that's continuity. Limits just have to look like they're going somewhere. Continuity says you actually have to get there. Right? Fill in the hole. Cool.
So then at 0, is that continuous from both sides?
Yeah, 0 looks a little funky, right? And it's going to have some problems later in calculus. This is called a cusp. You see how it just suddenly turns? So if you actually did that in a plane, you wouldn't be alive anymore. You can't, human body can't take that kind of turn. So there should be some kind of problems with something related to velocities and stuff. Maybe some rates of change that we're going to get into, right? But as far as continuity is concerned, I don't have to pick my pen up to do that. My finger in this case. I don't have to pick my finger up. So it's continuous all the way from here to there. It's continuous. So from -2 to 2, this thing, that's one area where that thing is continuous. You with me? It's got that's a little funky. It's called a cusp. Because it turns very quickly, right? But it's fine. As far as continuity is concerned, it's fine.
The question says, though, is it continuous from the left or from the right or neither?
Yeah.
It's continuous from both, so...
Yeah, there it's definitely continuous from both, but don't go crazy. You don't have to talk about every point. The part B is just going to be concerned with these definite kind of places, right? Yeah, anywhere inside of a line is going to be continuous from both sides.
Well, I would just assume 0 was one of the numbers that it was asking about.
No, because there's no problem at 0. There's no jump. There's no going to infinity. It's fine. It's got this hard turn, but continuity just says, do I have to pick my pencil up? No. Okay.